What's going on, guys? Welcome back to Pinehurst Online Teaching. We are talking about implicit differentiation today, and you probably wondering what it means. Yes, it means study time. Okay, so we're gonna start off with a couple of vocabulary, so people, try to understand what's the meaning of the sentence up here, implicit differentiations. So vocab, okay, so along with the vocabulary in maths, will be slightly different from the vocab you learn in English, because the vocab in maths goes with the example. Let's say, let's talk about the meaning of the word, explicit first, because that is the opposite of implicit, I must say. Okay, so firstly, what it means by explicit differentiations. So we're going to start with a big word, explicit differentiations. So the meaning of this guy is actually what we always do because we have the formula between x and y. We always have them. So let's say we have y is x squared plus x to the power of 2020, which is this year. Okay, so now the explicit differentiation means that we can differentiate y with respect to x using the chain rule. In this case, it's going to be a chain rule anyways, because the function is not basic itself. So I can write dy over dx. And you can see that because y is in terms of x, so that's why it is explicit, because y is written explicitly in terms of x. Whoa, that's a big sentence. So again, explicit differentiation means that y is already in terms of x, and now you're trying to differentiate y with respect to x, and the method we're using here is chain rule. So if I scroll some up a little bit, that's too much. All right, so I'm going to use chain rule here to differentiate. I'm going to make sure that I go from outside to inside. So outside I can see that, my first instinct is I'm going to use the power rule to differentiate. So I'm going to bring down 2020. So 2020. And then I subtract 1 from the power. So I got x squared plus x 2019. We're living in the past. All right. So, and lastly, we don't forget to multiply by the differentiations here of this guy in the bracket. So we're going to times by x squared plus x differentiated. Right. So if we put them together, so we keep this guy because this is what it is. So 2020 times x squared plus x to the power of 2019, and then times. So when I differentiate 2x, I got when I differentiate x squared, I have 2x, and when I differentiate x, I have 1. You should be differentiating like drinking water. It should become real fluid. All right. And this is the answer. So this is the answer to the explicit differentiation. So very nice and simple. You just need to make sure you use the chain rule effectively by doing a lot of practice, aka homework. Okay, so let's talk a little bit about implicit differentiation, what it means, right? So implicit differentiation means that you don't have y as a subject, and it is quite hard to find y as a subject. So let's talk about implicit differentiations. Differentiation. Differentiation. Look at the spelling right here. Spelling bee champion. All right. So we talk a little bit about implicit differentiation. Firstly, the word implicit means the word implicit. This one means. Let's just zoom out a little bit. If you can't see clearly, time to visit an optometrist to make sure that you can see things clearly. Okay, so implicit means uh, Y cannot be or hard to write in terms of X. Fairly simple. Um, I'm gonna do two columns here. So explicit, and implicit column here. So you see what's going on. So explicit means Y is a function in terms of X, which is what we always do anyways. You know, you've been differentiating for centuries and you probably know how to differentiate Y equals Fx effectively. We have three methods. We have chain rule, we have quotient rule, and we have product rule. So those three methods is absolutely, blow your mind away when we do explicit differentiation. But now we talk about implicit differentiation. It's different, why it's just hard. It's just like why is hard to write in terms of X. You go. So we move on from here. So what does it really mean? Like what does it mean? You've been asking yourself, like, what is it on about? Why is it so hard to write in terms of X? So to understand why it's hard to write in terms of X, I'm going to give you an example right here. Okay, so for example, e.g., it's gonna be like something wacky like this: x to the power 3 plus 3y squared equals 4. Now you can clearly see from here, it is still possible to make y the subject, but you're gonna have to answer because y squared is gonna be like what? Plus and minus, two different functions. Things are getting more complicated. So how do we overcome that difficulty? That is exactly the lesson today. All right, so let's get to it. Now you have all the tools that you need in the world to do, explicit differentiation. We are talking about implicit differentiation today, and this is a big thing. The next big thing of 2020 besides coronavirus. Okay, let's get to it. Now let me demonstrate how to differentiate x cubed plus 3x plus 3y squared equals 4. So let's go over a quick example. Phi dy over dx in x cubed plus 3y squared equals 4. Okay, so I'm going to quickly demonstrate to you how to use differentiation and chain rule in finding dy over dx. And obviously, you can, the first thing that springs to your mind is you're gonna make y the subject, and then So if you make y the subject, right, you will see, let's say, uh, naive thought, naive thoughts. So I'm gonna tell you right now, this writing path is blowing my mind. It's so beautiful. Woo. Okay, so naive thought is going to make y the subject, so I will do this 3y squared equals 4 minus x cubed. Y squared will be 4 minus x cubed over 3. Oof, that is some hardcore algebra right there. So if I move on, I got y squared will be, oh, actually, I'm finding y, what I'm doing. So I actually want to square root both sides. So I got plus and minus. So you can see that the trouble already. So 4 minus x cubed over 3. Yes, you can differentiate this, but you have two different functions because you have plus square root and you have minus square root. Which one do you pick? So hard, right? So complicated. It's hard to choose. Just like, you go to KFC, you want to eat chicken wings or chicken legs. It's hard to pick because they're all tasty. Okay, so now what we're gonna do here is you're gonna use the chain rule effectively. We're gonna make sure that the chain rule is in the action. Let's write out the question again. X cubed plus 3y squared equals 4. So x cubed plus 3y squared is equal to 4. Let me put a line here so you can see. This is the next big thing. All right. So x cubed plus 3y squared equals 4. Now, I want to find dy over dx. Yes. So I will make sure I differentiate the left hand side and the right hand side in terms of x. So I put d, the whole thing, x cubed plus 3y squared over dx. So literally, this left hand side means I am differentiating with respect to x. And I have here d over dx. This d over dx means I'm trying to differentiate with x being the variable. Just like usual explicit differentiation. I was going to write this way because it will make more sense if I write this way, and you will see later on. So d over dx, basically, this d over dx here is nothing too fancy. It means that you are trying to differentiate with respect to x, and you're treating x as the variable. So if I move on from here, I can see that I can differentiate the x cubed separately with 3y squared because of the plus, so I don't have any problem. I can just differentiate them separately. So if I treat them separately, it will look like this. Right? Don't be too surprised. It's gonna be so good, x cubed then plus d 3y squared over dx equals, well, in here, look, you have you differentiate a number with respect to x. Well, you know what happens when you differentiate a number? It will become 0. Come on. Yeah, this guy will become 0. Okay, if I move on, I will see that, when you differentiate x cubed, you're gonna get 3x squared. Surely. Textbook problem. And then, oh, this is the big thing, right? This is the big thing. You see 3y squared and you see dx. They literally have nothing to each other's, right? 3y squared, there's no x in there. In fact, y is a different variable to x. So you gotta borrow, right? This is the real trick right here. This is the $1,000,000 trick. You gotta borrow this dy. Yeah, you see that? Oh, look at this. I got 3y squared. I differentiate with y. Oof, things just get better together. And then because I borrow this dy at the bottom, I have to put back on top to make the world balance, right? And then I keep dx. Oh, you see something happening right here? I see joy. Look at this dy over dx here. It appears out of the blue. Nah, it doesn't appear out of the blue. It's my intention. Equals 0. Okay, here we go. Here we go. Again, this is a big thing, I'm telling you right now. If this is not big, I'm not sure what else is big, if you know what I mean. So 3x squared plus this 3y squared. If I differentiate 3y squared with respect to y, obviously, so it will become 6y, right? Usual differentiations. Well, that's dy over dx. is locked in. And now I want to make sure that I make dy over dx the subject. So I need to isolate dy over dx. Literally from now on, it's just simple algebra. If you're passing the year 10 algebra, you can make sure that you bring this 3x squared on one side. So I have 3y times dy over dx equals minus 3x squared. And then I divide both sides by 6y. So I have minus 3x squared over 6y. If I simplify this fraction a little bit, then I have minus x squared over 2y. And this is my answer to dy over dx. This is my final answer to dy over dx. The similarity and the differences you can see from here is that dy over dx is not just x. It's not just a function in terms of x. It's a functions depending on x and y. That is why we call that implicit differentiation for a reason. All right. So let's recap again one more time. What is happening here, guys? All right. So recap everything one more time. So we're going to go over more example in the class, but for now, this should be a very short introduction to what it means by implicit differentiation. So explicit differentiations. I'm going to write short here. It's supposed to be a straight line. Implicit differentiation. All right, here we go. So let's say y, it will be x to the power 2020. So when if I do y over dx, you can see that I have 2020 times x to the power 2019. As you can see from your right hand side here, the one that I just bubbled this differentiation depends on only x because it's explicit, right? Oh, I missed out the I here. Okay, but for that example that we've done above, we got x cubed plus 3y squared equals 4. Our dy over dx looks a little bit different, right? Our dy over dx is actually let's have a look here, minus x squared over 2y. And there you go. You can see that the answer to implicit differentiations is a combination of x and y. That's why we call it implicit differentiation. The explicit differentiation means your result only depends on a single variable, aka x. But implicit differentiation depends on, it could be either x, could be y, or could be both. Sometimes it could be, x, y, z if we have 3 variables. So there you go. That should be enough for the introduction. Now let's do some work. And remember, yes, we do apply the product rule and quotient rule effectively. In fact, I will write the form for the quotient rule and the product rules here so people might have a look at what might become when you use implicit differentiation. So to recap the rules and recap all the rules. So recap. So if you d over dx, f plus g. So here I call f plus g, f and g, they are 2 different functions. They could be the same, but this is the idea. So df over dx plus dg over dx. So this is literally just saying you are differentiating f and g separately. And if I put a negative to it, we'll do it. Yeah, there you go. Nice. Easy peasy. So what if you use, you'll be asking yourself, what if you use the quotient rule or the product rule? Here we go. So this is for the product rules. So du dx f times g is going to be df over dx, which is basically means you differentiate f, and then you times g, and then you plus f times dg over dx. Well, it can make sense. So f dash g plus f g dash, that kind of thing. And the quotient rule. Well, we try not to use the quotient rule for this. You can always make it like a product rules like this. I'm gonna give you an example. Quotient rule, quotient rule, quotient rule can always be turned to product rules. This is the golden idea, product rule. Here we go. Be like, what is this guy talking about? Quotient is quotient and product is product. What's happening? Okay, so I'm gonna give you a big picture right now. So let's say we have this problem here. It will be x squared plus y over, what's that? It's gonna be x cubed, or yeah, let's do x cubed then, equals 6 sine x. It'd be like, oh, okay, so actually, yes. So you are finding dy over dx of this guy, and you're like, oh, let's see a quotient here. Fear no more. You can always bring this guy up to make x squared plus y is 6 sine x times x cubed. And now you can use, the product rules for this. You see that's how you turn a division into a multiplications. Yeah, that's it. See you soon.